Well, let's start by what did we do last time? Last time, well, we defined orthonormal bases, or an orthonormal basis for a subspace. And just to remind you, a basis is an orthonormal basis provided the vectors are all unit and then they're all orthogonal to each other, right? And then we also talked about orthogonal projection, which if you have a vector in Rn and you want to project it, the orthogonal projection onto some subspace, well, the formula that we came up with, it used an orthonormal basis for the subspace. And then we also talked about orthogonal complement, for example, and a few other things. But if I had like a theme for the last section, it would be that orthonormal bases are wonderful bases. So the theme, or what you should take away from that, of course, we had lots of calculation, which is an important part of understanding, but orthonormal bases are the best kind of bases. Okay. So this brings us to today. Suppose we have some subspace of Rn, and I call it W, and you have some basis. And B, this basis can be anything provided it's linearly independent, the vectors, and spans, but not necessarily orthonormal, not necessarily orthogonal even. How do you find an orthonormal basis for your subspace? And this is the topic of today. We see two vectors in R4, and V2 is not a multiple of V1, neither are 0, linearly independent. The dimension of W is 2. And what we want to find is U, which is, say, U1, U2, that is an orthonormal basis for W basis. Okay, well, how are we going to do this? Well, this is different than the last video. If you take V1.V2, we get 100 minus 75, 25. So these are not orthogonal vectors. We had an orthogonal basis, and we just divided each vector by its length, and this got an orthonormal basis, but we can't do that here, for example. Like I mentioned, it's not orthogonal. But we can start in a similar way. Namely, to get U1, this is the easiest one to find, we just take V1 divided by its length. And we can calculate here, for instance, the length of V1 is the square root 16 plus 9 is 5. And so this vector U1, maybe I will write it in blue, is 4 over 5, 0, 3 over 5, 0. Okay, so we have the first vector in our orthonormal basis. But the problem is, what are we going to do here? How are we going to get a second vector? Well, this goes back to what we began in chapter 2, when you just have projection onto a line, and discussed in the last video. So what we're going to do, let's suppose, so here's a picture. I'm not going to try to accurately represent these two. It's just an idea of what's happening. So say we have some V1, and then we have some here, V2. And what have we done so far? We have found, well, first of all, you see by the picture, they are not orthogonal. Okay, very good. But what we've done so far is we take V1, divide by its length, and we get a little unit, say U1. Okay, great. Well, how are we going to find the second one? I need a vector that is orthogonal to V1. Equivalently, it's orthogonal to U1. But the thing is, we know how to do this, right? If I project, so here, let's see, I need something that's about 90 degrees. If I project, okay, so there's two vectors here, and I one I will do in black. I have enough colors to show the different ones. The black vector is the projection of V2 onto the line. So if I take, for example, L is the span of V1, or, you know, I could have just as well have said L is the span of U1 because they are both along the line. It's fine like this. And then this black vector is the projection of V2 is in black. Well, of course, this is not going to be the orthogonal one. It's this one. So this vector, which is the component of V2 orthogonal to the line, is V2 minus the projection, which is what I just erased. Because what I'm really interested in is the green one, right? This is the one that's orthogonal to V1 and similarly to U1. But, well, so far so good on the orthogonal part, but this is not unit. And so the final step here is we will have U2 is this divided by its length. So this is how we will construct this second element in the basis. Okay, so let's do this now for this example. Okay, so well, I won't start with U2. We have V, the orthogonal component of V2 equals, well, V2 itself is 25, 0 minus 25, 0. Oops. And then we subtract, well, this is going to be a dot product. I'll write it underneath. Okay, so before I finish this, let me remind us of what the formula is for this. Well, we see it here, but I will include it with the formula for the projection. This right here, it's this. But then this part is U1 dot V2 times U1. And you look at U1 dot V2, well, we have, this is 20 plus 0 minus 15 plus 0. So this is 20, maybe I'll put that as a step, 20 minus 15. But we know this is 5. We know, very nice. This is 5. Okay, good. So now what I'd like to do, let's just compute this. We're almost done with this here. We just need to take the difference of these two vectors and then divide by the length. Well, here, this is 5. When you multiply here and here, you get 4, well, 0, 3, 0. So if I have 25 minus 4 is 21, and then I have 0. Minus 25 minus 3 is minus 28, and 0. Okay, getting closer, but this is definitely not a unit vector because, well, look how big those numbers are, right? So now we can compute its length. Maybe I'll continue in black. The length of this component of V2 that's orthogonal to the line is the square root 21 squared plus 28 squared. And I can just tell you it's 35, but I would not be able to do that in my head. I just remember it from my notes, okay? That was definitely a calculation for me. The final step here is, we know this, maybe I'll write it here, U2 is 1 over 35 times 21, 0 minus 28, 0. But maybe when I go to write my basis, which is what I'm going to do now, my basis U, I will bring this 1 over 35 inside some. But we have all the work. We have U1, we have U2. Now I'll just write this basis we're looking for, U. Well, it is here, 4 over 5, 0, 3 over 5, 0. And then when I simplify this vector, let's see, this is 7 times 3. I get 3 over 5. 0, minus 4 over 5, 0. And the neat thing is you can clearly see when you take the dot product of these two vectors, we get 12 over 25 minus 12 over 25, 0. So they are orthogonal and they're both unit. This is an orthonormal basis. What I'd like to do now is the next example. The question is, what if you have a basis with 3 elements or 4 elements or 5? What would you do next? So we understand, at least we've seen one example of finding u1 and u2, but what would happen if I had a third vector here? So to address this, I'm just going to take these exact 2 vectors, add one more in R4, and we will figure out the corresponding orthonormal basis for that vector space. Okay, you see I've added one vector, but let me just quickly go over how we would have begun. We take v1 over its length, and we get, in fact we have done this, it's going to be 4/5, 0, 3/5, 0. Okay? L is the span of v1, or equivalently, I can write it as the span of u1 because they're multiples of each other. And then I take u2 to be this, which was, we had 3/5, 0, minus 4/5, 0. And then I will just comment that where this vector equaled v2 minus, and then we take u1 dot v2 u1. Okay, it came from orthogonal projection. So this, so far in finding u1, u2, u3, is exactly like the first. Well, because u1 and u2 are literally the last example I just did. Okay, so we have u1, we have u2. What would I do next? Okay, so I have 2 vectors now that are orthonormal, and then this one, you can dot product with either one of these, and you will realize that this is not orthogonal to this is not orthogonal to this, right? So we can't just divide it by its length and be done. Well, we're going to do the same thing that we did for this one, except instead of projecting this just along a line of the span of v1, or just the line for the span of v2, that would not be enough. We will project this third vector. Oh, I should label these v1, v2, v3. We're going to project v3 onto the span of, well, the previous 2. So now we're going to project this onto a 2-dimensional subspace in R4, and then take the component of v3 that's orthogonal to that subspace. And this will work because if you're orthogonal to a subspace, namely the one spanned by these 2, that is equivalent to being orthogonal to the basis vectors, or the vectors in a basis, I should say. And so you'll be orthogonal to both v1 or u1 and u2. Okay, so now let's write that down. So what I'm going to do is I'm going to let v be the span of v1 and v2, and this is the same thing. I'll just write it even though I don't necessarily need to. It's the same thing as the span of u1 and u2. Okay, it's the same subspace. And then we want to project, just like I said, v3 onto v, and then we will have this third unit vector will be, you take the component of v3 orthogonal to the subspace and divide it by its length. So this component of v3 orthogonal to the subspace will be orthogonal to this, orthogonal to this. And these are already orthogonal to each other. Then we divide by, its length. Now it's unit. So all of a sudden we will have an orthonormal basis. We will have 3 orthonormal vectors for this 3-dimensional subspace. If you're orthonormal, you're literally independent. So we will have a basis. Well, and maybe I should have even added that it's very clear that the dimension here of this subspace is 3. Just by arguing with zeros, right, you can see that this third vector is not a linear combination of the previous 2. So in fact, these are linearly independent, right? Okay, that was just a comment. Okay, well now, maybe I should just mention one more thing where, now let's recall what this is. This V3, the component of V3 that is orthogonal to the subspace is just V3, but then we subtract, well, what would it be? It would be subtracting, I'll write it above, the projection onto the subspace of this vector. But what is that, right? Maybe I'll put parentheses this time. What is the projection? This is what we did last time. Well, I want to use the u's because they're an orthonormal basis for this V. So this will be V3 dot U1 times U1 plus V3 dot U2 times U2. Okay, I had to make sure I closed every parenthesis that I opened. And this will be here, this component of V3 orthogonal to this subspace, then divide by its length. Okay? If you need to pause the video and take a deep breath, you have my permission. Okay, here we go. Well, it's not too bad. It just seems like it's intense the first couple of times you do it. So let's write V3. It's here, 0, 1, 1, 1. And then I will subtract. Okay, now I need some dot products. U1, I have 4 over 5, 0. 3 over 5, 0. And then I'll go ahead and do this, then I'll write the dot products. And then U2, which is 3 over 5, 0. Negative 4 over 5, 0. Okay, so now I just need to compute V3.U1, V3U1. You see it's 0, 0, 3/5, 0. Oh, I didn't have to leave so much space. In fact, maybe I should back it up so I have more space later. So this is just, I left a lot of space just for the number 3 over 5. And then I'll recopy this. If I was using my notes app, as you might have seen in the example videos I make when people ask me about homework problems, I could just pick it up and move it. I wish I could do that sometimes on the whiteboard. Oh, this was positive. But a whiteboard I have to erase, recopy. Okay, then we have, what's the dot product here? V3 dot U2. Well, it's 0, 0, minus 4/5 and 0. So this is minus 4/5 and then times this vector, which again I'll recopy. This was 3/5, 0, minus 4/5, 0. See, now by optimizing my space, I can actually do this sum on the same line. Well, what do I have? Oh, I have 3 things. Well, let's do it entry by entry. First, this is 0. Okay, fine. And then here I have, this is minus 12 over 25. Oh, hold on. I forgot my parentheses. Now we should be okay. Let me comment what I had to change when I rewrote, and I don't know if I had it wrong before either, but you see it's minus the projection. So here's this minus here, minus parentheses, here's the projection, right? And I had left off parentheses, and that would have had me calculate wrong. I would have had like a minus sign off here, which would have made everything incorrect. So it's minus the projection is a sum. I have minus the projection is a sum. Okay, now we should be good. So maybe I'll compute what's in here, and then I will take this minus that. So what's in here, I have 12 over 25 minus 12 over 25. This is 0. 0 minus 0 gives me 0. Okay. Now I'm on the second entry. I have 0, 0. 1 minus 0 is 1. Okay. The third entry, I have 9 over 25 plus 16 over 25. That's 25 over 25, 1. Then I have 1 minus 1. Okay, I am 0. And finally, the fourth entry, well, 0, 0, 1 minus 0 is 1. Okay, so this, well, and you can check, it's very clear that V3, well, the orthogonal component of V3, I should say, that it is, in fact, orthogonal to both U1 and U2, just looking at the zeros, right? But now it's not unit. In fact, if you think about the length, it's the square root of 1 plus 1, square root of 2. So maybe I'll write that here. This length is the square root of 2. And so our final basis vector, U3, it's here. It's 0, 1 over the square root of 2, 0, 1 over the square root of 2. Okay. Now we will go back to the top and write our orthonormal basis. Here, U. And then we're going to talk about this process in general, what we have done. So maybe I will do U in blue. U is here, 4/5, 0, 3/5, 0, then 3/5, 0, negative 4/5, 0, and then here, 0, 1 over the square root of 2, 0, 1 over the square root of 2. Okay, and you can tell, you can check that these are all, well, it's an orthonormal collection, okay, of vectors. Very nice. This is what we're looking for. This is called the Gram-Schmidt process, and let's discuss how we do it in general. Okay, so we are given a basis V1 to Vm, which is a basis for a subspace W of Rn. And then we will find an orthonormal basis. We will find U, which is U1 to Um. This is orthonormal basis for W as follows. Okay. Well, guess what? It's exactly what we've just done, except sometimes you have more than 3 things in a basis for W. Okay, so maybe I'll do this in steps and I will try to color code them. First, well, U1 is the easiest. It is V1 over the length of V1, okay? And then, as we saw in the first example, we let L be the span of V1, which is also the span of U1. Okay, I didn't necessarily have to write both of those, but I did just to make a point. And then, now I'm ready to tell you the next step, U2. Is this. It's the component of V2 that is orthogonal to the line divided by its length, where this is V2 minus the projection of V2 onto the line. Okay, so far so good. Well, then we would continue. This process is very nice because at any step J, where J goes, well, technically between 2 and M, you construct Uj based on the previous J minus 1 vectors that you have made. Okay, so that's what I'm about to state. Just like we saw, right? We just did an example. We found U3. We took V3, projected it onto, well, it was the plane spanned by U1 and U2, and then took the orthogonal component of that and then divided by its length. And this is what we do in general. So let me just tell you the Jth step. Okay, so then I'll put a little ... for, let's say 3, although I could have put a 2 here, although I've told you what happens at the second step. J less than or equal to, we have M things in our basis. What I'm going to do is let's let V be the span of V1 to Vj minus 1, the ones that have come before, which is also equal to, and this is what I was starting to say, the span of what I have found so far, U1 to Uj minus 1. And the nice thing is U1 to Uj minus 1 is an orthonormal collection of vectors. This, in fact, from what I just said, these J minus 1 form an orthonormal basis for V. Okay, so then, now I'm ready to tell you how to get Uj. Uj, we take the orthogonal, or the component, excuse me, of Vj orthogonal to this subspace, divide by its length, where this is Vj minus the projection of Vj onto the subspace. And this, projecting on a general subspace, this was the last video, right? Orthogonal projection. Now, this is how we do it. So we do this all the way to the very last one. And then we have this collection, U1 through UM, which are all orthogonal to each other and their unit, because I've, I forgot my one symbol here. Good thing I was looking at this. Now it makes sense. Okay, there's a lot of indices and symbols in this section. Okay, now this is unit. I have taken this vector and divided by the correct length. Okay, so just as a comment, well, we're finished, right? We have U1 to UM, but as a comment, I will just say, note, this vector, and this is what we saw in the last example, we can write it like this, Vj minus, it's U1 dot Vj times U1 plus U2 dot Vj times U2 all the way out to it's going to be J minus 1 dot Vj Uj, okay? This is the, well, and I did it wrong. I was going to distribute my minus. This is the same thing I had before. I could either have it like that with a big parentheses, but I will go ahead and distribute the minus so I don't have to worry about that again. So this is the formula where you take Vj minus the projection, and I distributed the minus. Now I think it's correct. Okay, so this is how we calculate this, or one way to write this. This part is negative the projection, and then this is Vj, so we have Vj minus the projection. I'm going back to an example with just two vectors. So, well, in particular, the Gram-Schmidt process will not be too involved because I want to move into the other part of the title of today, which is QR factorization. And that's a lot easier to wrap your brain around the first time when you just have two vectors in your basis. Okay, and then I'll do another example where we have three vectors in our basis after that. But this is a basis for a two-dimensional subspace of R4 because the vectors are linearly independent. We can see that. Okay, well, let's begin. U1 is V1 over its length, and I should label these. This is V1, V2. The length of this is pretty clear to calculate quickly. It's the square root of 4, which is 2. So this is, if we write that down, it's a half, a half, a half, and a half. Because, maybe I'll put that over here. I'll put it here. This length was 2. Okay, so far so good. Well, now we need to compute this. The component of V2 that is orthogonal to the span of U1, or the span of V1, it's the same line. And this was, okay, V2 minus, we take U1 dot V2 times U1. So let's write this here. This would be, okay, don't look at this stuff yet. What happened was my camera went out of focus at some point in the middle of the problem, and I didn't realize it until later. Okay, so I left it on the board. We're just going to talk about it, and then we will move forward. We want to compute this component of V2, which is orthogonal to the line spanned by V1, or equivalently by U1. So we take V2 minus U1 dot V2, U1. And this is where I think it kind of went out of focus. This dot product, we take U1 dot V2, which you see is 1 plus 1 plus 3 halves plus 3 halves. That's this. The dot product is 5. We multiply this by U1. So this is, well, initially it's just this component of V2, which is orthogonal to the line, where we take 2, this is now minus 5 halves, negative a half. 2 minus 5 halves, negative a half. This is 3 minus 5 halves, positive a half, and then similarly 3 minus 5 halves, positive a half. Okay, this is this part. Normally you would divide by the length and you have the unit vector, except when I go to calculate the length of this component of V2, which is orthogonal to the line, this thing, we get the square root of 1, which is 1. So we already have a unit vector here. And so in fact, this is U2. So we have U1, U2, and then let me write up here, I will even write my basis U here. My orthonormal basis is a half, a half, a half, a half, and then we have a half, oops, negative a half, negative a half, a half, a half. And it's quite straightforward to see that U consists of orthonormal vectors. Okay, that's the end of that example. But what I'd like to lead us into is something called QR factorization. And the question is, and I'm purposefully not trying to show you the details until I'm ready to talk about it. The question is, what does this say for matrices? Okay, so if I take the vectors in B and put them as columns in a matrix, A has linearly independent columns, and what we want is A is Q times R. This is called a QR factorization, where Q has orthonormal columns. And I will say in every single QR factorization, the Q is what you get through the Gram-Schmidt process. A is the columns of, well, you know, the columns are the vectors in your original basis. So far, nothing is new. We have A, we've been calculating Q. Well, it's new as of today, but I mean, it's nothing new I'm writing down. But the question is, what is R? Now, at the very end, so I'm about to do some stuff that's a little bit, well, it looks a little bit technical. Then I'll define the QR factorization for a general n by m matrix A. But the way that I personally would calculate R, the matrix R, that I will show you at the end after we do one more example. And it's what we're really moving towards in the next section. And I think it's an easier way than where our, well, what we'll see right now. But what I will say right now is the matrix R, in a sense, we've already done the work to calculate it, although we have to realize that we have. So if I translate that to this problem, it says, here's A, here's Q, and if you think about size, this is 4 by 2, this is 4 by 2. It means that R must be 2 by 2. In order for the product to be defined, you need this 2. In order for its product to be 4 by 2, you need this 2. So here we're looking for a 2 by 2 matrix R. So here I will write the specific one for this example, okay? And here I will write sort of the general R when you have 2 columns in A, or 2 vectors in your original basis, for example. Okay, so I'm going to talk about this, and so we will fill these in sort of at the same time. Let me erase some of this just to give myself space on the board to write. Now, let's look at this very first equation. Well, first of all, before I look at any equations, let's try to understand what's happening here. So here, the columns of A are V1, V2, and the columns of Q are U1, U2. And let's think for a moment about take row dot column. This would give us this one, and then row dot this column, this one, like this. Let's start thinking about the first column, okay? And that's going to come from this equation. So if I multiply through, what do I see? I see that V1 is the length of V1 times U1. And here, this is a number and this is a vector. So this column is a multiple of this column. That's what this is saying. What this equation says is that this first column of the matrix R must be this. Okay? Now, what is it in this case? And then we can check. This is 2, and this is 0. And in fact, you can check. Here we have 1 plus 0, 1 plus 0, 1 plus 0, 1 plus 0, and you see it's all ones here, right? Okay, so this is the first column. This is generally, like I said, when A has 2 columns, and this is for my specific A. Okay. Okay, well now, I need to figure out this second column, and what it's going to use is it's going to be, this was an equation that related V1 to U1, and really it was like a 0, U2. And that's what gave me this 0 here, or here. So I'm going to have an equation that relates V2 to U1 and U2 that helps me fill out what's in this second column. So let's figure out what that equation is. Well, it's going to come from this, that if I take this, that's not exactly U2, but I take this and divide by the length, then I get U2. So it's going to be a two-step thing here. Okay, so from this, we get that U2 is 1 over the length here. 1 over the length, well, times this thing. This is equal to this. Times, we get V2 minus U1 dot V2 U1. Okay, and I think I closed all my parentheses. So I'm going to erase some of this. Uh-oh. Let me recopy what I started to erase. In our example, we had U1 dot V2 is 5. It's literally right here. Okay, I'm just copying it up there because I'm about to see that formula appear. Okay, then I'll leave that link, that's fine. Okay, here we go. Now let's take this equation right here, second one, solve for V2, because as I mentioned, I want to get V2 as some combination of U1 and U2. It'll tell me what to put in these two entries. We're going to get V2 equals here. Well, if I multiply through by this length and then move this over here, I get the following. U1 dot V2 U1, and then plus the length of this U2. So this equation and this one are what I use to find my matrix R. Now what does this say? V2 is this U1 plus this U2. And again, if you think how matrix multiplication works, we would have in this column, we would have U1 dot V2 and this length. So let's fill it out here and we will check. So this is why I left it on the board, or recopied it, I should say. And then the length here of this component of V2 orthogonal to the line was 1. We verified why this column was all 1s, and now let's verify that this column should be 2, 2, 3, 3. Well, it's each row dotted with this column. We have 5 halves minus a half, 2. 5 halves minus a half, 2. 5 halves plus a half, 3. And 5 halves plus a half, 3. This R works and satisfies A is Q times R. And this form down here is general when A has 2 columns. But now let's discuss the QR factorization. What is the general statement about QR factorization that we just saw? Well, let's see, where we had 2 columns, right, in the matrix A. So here A is n by m. It has linearly independent columns. And then there exists n by m matrix Q with orthonormal columns such that A is QR. R generally, so we saw a little 2 by 2 R, but it will be upper triangular and it will have positive entries along the diagonal. Okay, and this Q, it's exactly what we get with Gram-Schmidt. It is the columns of Q are, well, there are orthonormal bases for the image of A, for example. If you take the span of all the columns of A. Okay, now you can say moreover, and this in blue is just one way to think about how to get R. But as I mentioned at the very end of today, I'll show you what I think is maybe a little bit easier way to find R. But here, if the columns of A, we have M columns are V1 through Vm. Okay, this was our basis that we start with. The columns of Q are U1 through UM. And then I'll just say R is this little r ij. Then this 1 entry is the length of V1. And then the diagonal entries, sort of from 2 to M, you take the length of these were the component of VI, that is orthogonal to, well here, this came from Gram-Schmidt, so orthogonal to the subspace spanned by the ones that came before. And then here, if I is less than J, that says the row is less than the column. This is this upper triangular part above the diagonal. You take UI dot VJ, okay? So I will do an example now where we have 3 columns, and then we will compute, well, Q and R, and then I'll show you another way we could compute R, okay? Now let's find the QR factorization. For this matrix A, we have 3 columns, V1, V2, V3. Our Q will have 3 columns, but they'll be orthonormal, right? And then this is what I just discussed, this formula, this upper triangular matrix R. We will have the length of V1 here, and then these lengths are for the components of these 2 vectors that are orthogonal when we do the projection. So for this one, it's just having projected on the line spanned by V1, and for this one, it's having projected on the plane spanned by V1 and V2, right? Okay, and then here, these dot products also appear, and the off diagonal zeros below the diagonal. Now, the way that I'll go about filling this out is, well, first I'll compute U1, and as I do, I fill in the first column. Then I will compute U2, and as I do, I can fill in the second column. And then finally, I can compute U3, and as I do, I can fill in the third column. And this is an easier way to do it rather than just totally computing Q and then having to go back and figure out what all these quantities were. So we can fill in R as we go through Gram-Schmidt. Okay, well, the first one is the easiest always. U1 is V1 over its length. And here, if we calculate, maybe I'll do some things in different colors, the length of V1 is the square root 1 plus 49 plus 1 plus 49. Okay? And this is the square root of 100, which is just 10. Okay, well, look, we're going to do this now. I don't even have U1 yet, but I know this length is 10. So I have the first column of my matrix. But now let's write this. This is 1 over 10, 7 over 10, 1 over 10, and 7 over 10. Okay, I had to write that kind of little. Didn't have all that much space because of this square root here. We have U1. Well, now let's move on. And the first thing I need, right, is V2, this part, this component of V2 that is orthogonal to the line spanned by V1. And we can compute this. It's going to be V2 minus U1 dot V2 U1. Okay, so let's do that here. Well, V2 is 0, 7, 2, 7 minus, well, I'm going to have a dot product, and then U1 is 1 over 10, maybe I'll give myself a little more space, 7 over 10, 1 over 10, 7 over 10. Now, okay, then in red, I will compute this dot product, U1 dot V2. Here is U1. Here is V2. What do we get? Well, it's all over 10. And we have 49 plus 2 plus 49. Well, this is 100 over 10 or just 10. Okay, so here I put now I have put a 10 here. And then we have this entry of our matrix here. Put a 10 here. Okay. Now let's take this difference, which will be this. Well, this just, well, clears out the denominators, right? If you multiply 10 by all of these fractions, you get 1, 7, 1, 7. So that's not too bad. And then I have minus 1, 7 minus 7, 0, 2 minus 1, 1, 7 minus 7, 0. This is this part, but it's not unit, right? In fact, maybe I'll also put this in red. The length of this orthogonal, the component of V2 that is orthogonal to the line is, oh, let me move this up some, is just the square root of 2. So now I haven't even written down U2, but I have the next entry in my matrix. This is the square root of 2. Okay, well, maybe I will put U2 here in black. And then I'll put a bar, work over here for U3. I think that'll be nice. I take this and multiply by 1 over the length. So I have negative 1 over square root 2, 0, negative 1 over square root 2, 0. And I didn't need that much. Now let's put a line. Okay, now I have this side of the board for U3. So far we have U1, U2, very nice. And for instance, if you take U1 dot U2, look, you have minus, and then minus, oh, okay, good. Good thing I checked my work. I was gonna say, oh no, they're not orthogonal. But you see, this is a positive one, and this entry should be positive. And now we actually do, this is minus, and this is plus of the same quantity, and then 2 zeros. Now we have it right. U1 and U2 are orthonormal. Okay, well now what we need, this part I was doing in blue, we need this, except this is not projecting on the same line or even any line. This is the component of V3 that's orthogonal to the plane spanned by U1 and U2, or V1 and V2 if you want to think about it that way. But the formula is this, minus, okay, we're going to have U1 dot V3 times U1, and then minus U1, U2 dot V3 U2. Okay, now let's write what all these vectors are, and we will have this computed. V3 is, here it is 1, 1, minus 1, minus 1. And then what's this dot product? Maybe I should do it below in red. Oh, yeah, okay, I'll go ahead and do this and then fill it out. U1 dot V3 is, here's V3. Here's U1. We have 1 and 7, 8 over 10, minus 1, minus 8 over 10. Oh, this is 0. So we're going to have minus 0 U1, which I don't really need to write it. 0 times any vector is 0, but I will include it for the sake of being complete. And I know another entry in my matrix, because what did I compute? U1 dot V3. I have this entry. And then finally, what I need in red, I need U2 dot V3. Here's U2 dot V3. Let's see what we get. We have, this is negative, this is 0, and another negative and 0. So this is negative 2 over the square root of 2, which is the same thing as negative square root 2. Let's see, I am coming down to almost having my matrix R. This is negative square root 2. Now if we write this here, well this is, oh, okay, look. We have minus, this minus, it turns into a plus. So it's going to be plus the square root of 2 times, here is U2. Here, okay, so this is negative 1 over square root 2, 0, 1 over square root, maybe I can leave a little more space. This is 0, 1 over square root 2, and 0. And now, I think I have space for this sum because this term is 0, and so what do we get here? We have 1. Well, when you multiply through by square root 2, this is minus 1 and this is 1. So we have 1, minus 1, 0. We have 1, minus 0, 1. We have minus 1. This is plus 1, 0. And then minus 1, 0, 0. This is minus 1. Okay? Now, again, not unit, right? In fact, we could write the length, maybe we will here. It's pretty easy to see. I'll do it in red to match all of the ones we were calculating. Oops. Oh yeah, okay, we're okay. This length is the square root of 2. And so this final entry in our matrix, see, we have found R, square root 2. And now all I need to do is write down U3 and we will have Q. I will write down Q here. This will be where I put Q. Maybe right up here is where I will write U3 just to finish this. I take this, I divide by the length. So this is 0, 1 over square root 2, 0 minus 1 over square root 2. And now I'm ready for my matrix Q because, well, I know what the columns are. They're U1, U2, U3. Q is over 10, 7 over 10, 1 over 10, 7 over 10. And the next column is negative 1 over square root 2, 0. 1 over square root 2, 0. And the last column is 0, 1 over square root 2, and then 0, negative 1 over square root 2. And you see, well, you could take any of the two columns if you wanted in Q and take their dot product, and you will get 0. And similarly, the length of each column is 1. Okay, so, well, it's very color-coded, but it's also a lot of calculation. But we have found Q, and we have found R. We have found the QR factorization of A. I left Q on the board, and I probably should have left A on the board, but I'll recopy it when I get to it. Now, what I'm going to say today is a focus of next time. So if you want to stop watching now, and then, well, start working on the homework for this section, you're ready for it. But I wanted to talk about what I find is an easier way to find the matrix R. Okay, you don't have to remember, for example, you don't have to remember what the entries look like. That pattern that I talked about down here in blue when I was talking about the QR factorization. You don't have to remember that, okay? So how do I find this? Well, first, let me talk about this equation. A is QR, and we want to find R. Well, okay, very nice. We just talked about how to do that. But what do we know about this? We know the orthonormal columns. In particular, the columns are linearly independent. So if it happens to be, if A and Q similarly are, let's say, n by n square, then you would be starting off with a basis for Rn, and Q is now an orthonormal basis for Rn, but in particular, Q is a square matrix with linearly independent columns. So you would get Q is invertible. And if you are in this situation that Q is invertible, then this is very nice, because then Q inverse A would be Q inverse QA, QR. Q inverse Q is the identity, which is just R. So now you see we have a found R, right? R is Q inverse A, and once you know Q, in principle you can calculate its inverse, and then you just multiply in this order, and order matters here, and you get R. But usually, or quite often, we're not working with all of Rn, we're working with a subspace of Rn, and so A and Q are not square. In fact, I didn't have any square A's or Q's in any of my examples. I was always having either 2 or 3 vectors in R4, right? But the nice thing is we can still do something like this to find R. And now we will define the transpose. So definition, I will just define it in terms of Q because that's what matters now. And then I'll talk about the transpose in more generality next section. In fact, it's a big focus of next section. So Q transpose is a matrix whose IJ entry is the, maybe I should put parentheses, is the JI entry of Q. And this is called the transpose of Q. Okay, so what are you doing here? You're interchanging the rows and columns. So if you start, for instance, this is the first column of Q, it'll be the first row in Q transpose. This is the second column of Q. This will be the second row in Q transpose. This is the third column of Q. It's going to be the third row in Q transpose. Okay, well, why is this nice? So what happens if Q is some U1, here are now the columns, U2, out to UM, columns, orthonormal columns. Okay, then, well, Q transpose, now I'm going to write it this way. This, I'm thinking about it as a column vector because it's a column of Q. So if I now make it a row, the most natural way to write it is like this. U1 transpose, right? This is now the exact same vector as U1, but instead of it being a column, it is a row, okay? And then U2 transpose all the way to UM transpose, okay? So far, so good. And entry of Q transpose Q is, this is the beauty of, I told you that we loved orthonormal bases, and this is another reason why, and we will pursue it more as I mentioned next section. Okay, the IJ entry is, well, here you take row dot column, right? So this would be UI dot UJ. Okay, you could put the transpose, doesn't really matter. Now I'm just thinking about them as being vectors in Rn. We know what this is. These are orthonormal columns. So this is 1 if I equals j, and 0 if I is not equal to j. So what do we see about Q transpose Q? Look, the entries are 1 along the diagonal, 0s everywhere else. This is the identity. This is the only matrix that looks like this. 1's down the diagonal, 0's everywhere else. I'm just going to erase and I'm going to write the exact same thing, except I'm not saying that Q is invertible because it's usually not square. So we're going to be still here, orthonormal columns. Okay. Want to find R. Very nice. Yes, I do. Okay. So what I'm going to do, look, well, let me just write it this way. QR equals A, then Q transpose Q, R is Q transpose A, right? But this Q transpose Q, because Q columns are orthonormal, this is the identity. So R, which is the identity times R, is this. So look, this allows us to find R by multiplying here. And this does not need that Q is square. This is usually the way that I would do it personally if I needed to find the QR factorization of a matrix, which sometimes I do. Well, you have to in your homework. I would first find Q by Gram-Schmidt. Then I just take its transpose, multiply by A in this order. And then you have R, okay? It's, in my opinion, is much easier than remembering exactly the way that the entries work in the matrix for R. So now let's just compute Q transpose A. Maybe I'll do it in blue. So Q transpose A is, okay, we have to be careful. This is our first example of a transpose, but you have many more starting with the next section. So what I always do is I go column by column. This is the first column. It becomes the first row. So this will be a 10th, 7 over 10, 1/10, and 7 over 10. This is the second column. It becomes the second row. Minus 1 over square root 2, 0. Positive 1 over square root 2, and 0. And then the third column becomes the third row. 0, 1 over square root 2, 0, negative 1 over square root 2. And now I multiply 1, 7, 1, 7, 0, 7, 2, 7, 1, 1, minus 1, minus 1. Okay, now I can erase Q because I was able to read off the information. And now let's just compute. Well, first of all, this matrix product is defined. Look, we have, I'll write it above, we have 3 by 4, we have 4 by 3, and we will get a 3 by 3, which is the appropriate size for R. Okay. So let's take row dot column. This becomes 10. Okay, this row and this column, 10. Okay, this row and this column, this one is 0. Okay. Now I move on. Maybe I'll space these out a little better. Give myself space. 0. Okay, let's move to the second row. Well, second row here, 0. We do this one and this one. We get, no, 2 over square root of 2 is square root 2. And then here we get negative 2 over square root 2, which is a negative square root 2. Now I'm on the last row. And now here, okay, 0. And finally we have, so it's a 2 over square root 2, which is just square root 2. So you see, this is the R that we had, right? It matches. Okay, so this is one way. In fact, like I said, I think I find it a little bit easier because you don't have to remember the way the entries go, but you have two options. You either can fill it in as you're finding the vectors u1, u2, u3, as I did right before this, or you just find Q, which is erased, take Q Q transpose times A, and then you have R that way too.